We're going to look at a mod for counter. This is part 1, in which we'll look at the design and implement our system Verilog code from that. So, for this specific counter, we have an enable en that allows it to count. When en is 0, it's going to stay at whatever value it currently is. This system's going to have an output of 1 when the value is odd, so it's 1 at the values 1 and 3, and then a direction control. When D is 0, it will count down, such as 0, 3, 2, 1, 0, continuing from there. When D is 1, we count up, and we'll count up 0, 1, 2, 3, 0, 1, 2, 3, and continue. This translates to our state diagram you see on the right. You'll notice that when en is 0, we have D declared as X, I don't care. That's because it doesn't matter if we're counting up or down, if en is 0, we're not enabled to move. Our next step in the design process is to create our state table. This is a transposition of our state diagram, which is what you'll see on the left here. To implement our system, we do need to create our next state equations, which means translating our state table into our transition table using state encodement. So our state assignments that we're using are binary. 0 is going to be 0, 0, 1 is 0, 1, 2 is 1, 0, 3 is 1, 1. So each of those base states, 0, 1, 2, 3, get replaced with its corresponding value to produce our transition table. Using this information, we then treat our Q1 stars in the table as our output that we're doing first, and we'll transpose our minterms, or the situations where it has a 1, into our K-map. That produces the map on the left, which is then transposed into the expression you see on the top there. We repeat the process, mapping the midterms for our Q0 star output to our K-map and minimizing, resulting in our equation for Q0 star. Finally, we'll create our output equation. Knowing all our equations, we're able to develop our implementation. Let's look at what that would look like. To create our system Verilog implementation, we're going to stick on a mostly gate-level approach, meaning our DFF, our sequential logic device, needs to be encapsulated separately. This is a simple implementation of the D flip-flop with inputs of clock and input D, producing Q and Q naught, so Q and Qn. Since we will be dependent on our present state Qs, then we need to create an initial piece, otherwise when we're starting out we don't know what to do. We'll let Q equals 0 to start and Qn equal 1. Then on our positive edge trigger of the clock, we'll update Q and Qn based on our input variable D. Now that we have our D flip-flop variable, we can go ahead and start building together our main module. I went ahead and copied over our next state and output equations, as well as making a header that defines our problem. So we're going to build our system around these equations. Module. We'll just call it main in this case. It will have a clock, the direction variable, the enable variable. It's going to produce the output. I always like starting with end module immediately there, so we have it encapsulated so we don't forget. Then we can do our inputs and output. Now that we've declared our port lists interaction, we can create all the wires we need to implement our system. So we'll do wire Q1, Q1 not, Q0, Q0 naught. These are our present state variables. Then we'll need our next state. So Q1 next state, Q0 next state. In this system, we do use D naught and En naught. So we'll need wires for those. We'll add a note here. These are our next state variables. And then we'll do a wire for each one of our product terms. So Q1 is going to have 5, Q0 is going to have 2. So we'll do Q1, P1, Q1, P2, so that's our product terms that go into Q1 star. And we have 2 for Q0. Now we can start building up our gates to implement. We'll start with our knots. And then we'll go ahead and start doing our next state equation for Q1 star. So we have our 5 product terms, so and Q1, P1 is going to get the En, our D naught, Q1 naught, Q0 naught, and Q1 product term 2 is this one here, so we have an En, D, Q1 naught, Q0, our product 3, which is En naught, Q1, our product 4, which is our D naught, Q1, Q0, and finally Q1, P5 is D, Q1, Q0 naught, and we OR them together to produce our Q1 next state. So all of our product terms get ORed together, so it matches our expression. Go ahead and do our Q0 star the same exact way. We'll do our 2 product terms first. Q0P1 gets En naught, Q0, and Q0P2 is getting En, Q0 naught. Then we have our OR, Q0 next state, Q0, P1, Q0, P2. And we'll come back to out in a second. So we're going to connect these to our flip-flops. So we'll do our instantiation. So DFF, we'll do FF1 corresponding to our Q1. It's going to get clock. Our D variable going in is Q1 next state. The output is going to be Q1, Q1 not. You'll notice that I don't have dot notation. I have an OR clock D Q1, Q1 not, clock D Q, Q not. So I've got them aligned up. I'll do the same thing for flip-flop 0. And that's going to make those connections. Our final step is the output we have to deal with. In this case, it's just equal to a single piece. In order to make this function, we need some way to associate the out with Q0. We're going to use a gate that does absolutely nothing. We're going to use a buffer. So buff out Q0. That's going to allow that connection to be made. That brings together our implementation and our system Verilog.